Hello, everyone, and welcome back. I hope you have grabbed your lunch and or a lovely, marvelous snack and get ready for our Lunch and Learn session right now. We have Ryan Coffey, who is a visionary senior scientist at Stanford University. And to introduce Ryan, we've got Bill Wright from Red Hat. Gentlemen, the stage is yours.
Oh, thank you very much. And I'm really honored to have Ryan here with us today and to talk a bit about the Enterprise Neurosystem community, which is an initiative we've had underway for roughly about a year now. And Ryan is a member of that community, and we're very excited to talk about it today. I think what I'll do is I'll flip through the headshots and go straight to the agenda. We're going to talk a bit about the origins of the neurosystem community and what the objectives are and basically why we came together the way we did. Singularity architectures and container environments and how they work together. Then we're going to have Ryan talk about the SLAC AI proof of concept that we're all working on together along with Harvard Analytics. And then also have a brief question and answer session if any of you have any questions about this. So for background, I think it was roughly 4 or 5 years ago, I was having a conversation with America Movil. And at that time, Raul Reyes, who was the gentleman who was in charge of a large portion of their infrastructure, made it clear that Red Hat was in a very interesting position to contribute to the state of the art of AI and ML. And it was an interesting statement because, of course, I always thought we were relegated to the infrastructure side of things. And he enlightened me. He said, basically, it's really a synergistic ecosystem, and the infrastructure is just as important as the applications and the way they interoperate. And you should probably start taking a look at that. And so I took his advice, moved forward, and we started a focus group internally with Sanjay Ayagari, Narendra Narang, our CTO, Chris Wright, and a few other folks. And we started talking about what this all might look like. And then over time, it became evident that AI applications were being deployed all over the enterprise, but there was no integration or cross-correlation between all these individual instances. They were really almost like point solutions, but there wasn't any larger federation taking place or larger scale intelligence looking at the data. And so we decided to take a look at creating a business singularity. And this would be a stepping stone to a larger global vision, you might say. And so really to integrate all the different business functions in an enterprise and put it into a single framework, the cross-correlation engine or engines that would then in turn make recommendations to management and help with course correction, almost like a partner in the enterprise. And so really this would be AI infrastructure, you could say, both the AI models and the infrastructure itself connected to almost every business function. And really, if you think about the DIY models that are deployed and the vendor models, it's really a hodgepodge right now. And it's the kind of thing where we need to come up with an intelligent middleware layer or network layer that can basically take in all this data and then feed it back into the cross-correlation system. So what we're looking at here is really I guess you could say the joining of both the edge and the core from, I guess, an architecture perspective. And Ryan brought up a very interesting analogy about a week ago. And Ryan, I will steal this from you, but every time I do it, I'll mention your name. He held up his hand and he moved his fingers together and he said, is this the edge or is this the core or is this a unified system and a unified perception taking place when I rub my fingers together? And it was fascinating because that really summarized what we're trying to achieve. It really isn't about these disparate systems. It's the system of system approach, but really it becomes a primary intelligence. And I think, if you think about the decades, when medical science began to truly advance about 100 years ago, that really led to the emergence of computer science as we know it today. And you could, of course, trace it back further than that. But as we understand more about the human body, the more I think these advances are translated into IT and these different computer science functions. And so there really is an interesting crossroads between the two, and that's brought together quite a few folks in this community who look at it the same way. And it began, again, with telco and the scientific community, of course, with Ryan, but this is really applicable to all the different businesses that are out there, financial services and oil and gas and healthcare. All these different areas are going to require this kind of functionality. But getting to the global vision and what we've really been thinking about and talking about is climate change. And I know that's a very popular thing to talk about right now, but if you live in the San Francisco Bay Area, as I do and as Ryan does, given the wildfires and what we've seen firsthand, it really strikes home. It's not just a it's not something on the horizon, let's put it that way. And the whole idea behind this is if you can start in the enterprise and develop this with business value and have the enterprise help build it out and apply the resources necessary to create this kind of a wide frame, I guess you could say, architecture that spans all these different functions, you could then correlate it and take it forward and get into a global neurosystem that would basically monitor climate change in a variety of different ways, including satellite imagery, including space-based telescopes, all sorts of different interesting infrastructure that's really sitting out there waiting to be integrated. I mean, all these different components and elements around the planet are in place largely. How do we bring all that together? Well, it would be something just like this. And so that's really been the driving, I guess you could say, theory behind this and the way we've wanted to move it forward. And we have a wide variety of really interesting folks involved in this community. So it's been a lot of fun for me. And Ryan, I think I'm going to go ahead and turn it over to you to talk about the more interesting things. But here, I'll just real quickly show what we're looking at. And this would be a proposed singularity architecture. You can take all these different elements like government labs and enterprise research, cloud providers, university labs, and begin to create a network effect across all of them, federate their knowledge, and then basically create a cross-correlation engine in the middle. And the idea is to either create a single engine or series of engines. And we could also take a look at a federated intelligence and how to move that intelligence around between different models and different instances. We're talking about all that within our, I guess you could say, our central architecture committee right now, which is led by Dinesh Verma, who's the CTO of Edge at IBM Research. And he's actually been leading that group and talking about the different ways we could apply that intelligence in different frameworks. And when we talk about the way the models will be connected, we're trying to get above the standard and classical models, with a VPN, et cetera, and look for more of a application level security, an app-to-app security framework. We want the applications themselves to be exposed, but not the network in general. And so we're looking at new frameworks to basically enable the kind of security that'll be required for these kinds of environments as well, but also to reduce latency and to really kind of isolate any kind of security incidents to just a single application as opposed to the entire framework. And with that, I'm going to turn this over to Ryan. So Ryan, please introduce yourself and take it away.
Absolutely. So I'm going to go a little off script maybe because you just fed right into this, Bill. This idea of federated hardware. So I'm Ryan Kove. I'm at the Stanford SLAC National Accelerator Lab. By training, I blow things up with lasers, and by practice over the last decade or so, also try to calculate how we blow things up with lasers. The federated thing is really interesting, Bill, that you brought up, and especially this last slide with the security. Scientists don't usually think about security. And when I talk to folks at the high-performance computing in DOE, oftentimes we're talking about these large experiments that happen in the light sources. Like my home is in the X-ray laser that the SLAC accelerator supports now, called LINAC coherent light source. We do open science. We share our data. We share our data openly with all other researchers, except we don't really, because we actually are competitors. And so it's hard for us to really share within our smaller community, our more specific domain science. The thing that's actually easier for us to do is to inherit ideas from people who are in a different domain. And that's the thing that I think is so interesting about this network that you showed that connected labs and industry partners. And the broader you reach, the more you encourage real innovation. Because when I'm inside my own science domain silo, and I apologize, I'm riffing on this right now because I just came out of a meeting where this was the core topic. Why is it hard to collaborate in science? It's because all of my closest collaborators are my stiffest competitors. Whereas if I can reach out and reach into fusion science, or I can reach into climate science or radio astronomy, I can borrow ideas and we can actually innovate by applying new techniques across the barriers. So to me, that's why it's so incredibly important to build this network and have it really be all encompassing. But of course, if you're going to do that, you have to have the security. So those last two slides that you showed, Bill, I think are are fundamentally important. So I really wanted to just drive that home a little bit more, that scientists don't usually think that way, but we should. And what I want to use the next few slides to go into is this kind of poking, not fun at Richard Feynman, because he's sort of the idol of most physicists. But I do point out that his finger's pointing upward here. And although he said there's plenty of room at the bottom, his body language is smarter than his words, I think, here. Because I point out this article on the right here that essentially says we're running into the atomic limit. We've got processors that are so small, we need compute to increase. We're going to, as I'm going to show in a couple of slides, we're going to be producing data far faster than we can handle it. And our compute is going to have a very hard time growing. However, we have an awful lot of creativity at the top. And so this is where we can sort of weave together in this architecture that Bill was describing, hardware innovation. Because there are folks out there that are getting extremely creative about how you build chips, how you redesign chips so they're targeted for AI applications. Algorithm development. We're getting into the world of leveraging quantum computing for algorithms. That's going to open up an entirely new world. How do we wrap that into this network? And of course, software is the most wonderful place to put our creativity, because it's an art form. Software is absolutely perfect creative space. And now pulling all these together, that's how humans really solve the real problems that face us, is by pulling these three things together: our innovation in technology, our innovation in mathematics and science and ideas, and our innovation in art and software. Sorry, I put software with art, but I do really believe that. And so these three things come together to really tackle problems that we cannot foresee the solution. We need imagination for that. And that's where this cross-domain network can enhance and really encourage that use of imagination to tackle these problems in truly new ways. And that's why I'm so excited to be a member and joining this thing that Bill started with Enterprise Neurosystems, because this is the connective tissue. This is the network. This is the axons that tie every neuron together in this overall system. And it's the thing that I think is really going to tie our science together in ways that we couldn't do in the past, because we were simply too isolated. We were too much islands in the past. And so if we go down to the next slide, I'll introduce a bit our use case. SLAC, the reason I like approaching this from the perspective of SLAC, it's a particle accelerator. Yes, we used to do high energy physics experiments. Now CERN has taken that leadership in that. But one thing that SLAC still maintains its leadership in is accelerator development, which means, and to translate that for the open public, that means active automated control of complex systems using hundreds and hundreds of sensors that are distributed over 2 miles. So when I say accelerator R&D, think automation on a 2-mile scale with hundreds to thousands of sensors as your input, and you have a latency that's on the scale of milliseconds. Some things are going to be microseconds. And so that's what I mean when I say accelerator R&D, for the sake of AI in doing adaptive information and action. Our sensors are a little obscene. We are upgrading our accelerator to be a superconducting accelerator. That means that instead of running at a normal sort of video rate of hundreds of frames per second, we're going to upgrade to millions of frames per second. That is, I would consider that rather obscene from a multi-megapixel camera, as is shown here in the upper right. These cameras are becoming existent now, cameras that are capable of the millions of frames per second data rate. And of course, what do you do with such a data rate? And that's what's led me to this problem of how is science going to incorporate the emerging algorithm, software, AI, and hardware to help us solve this problem at the source of the data. Because most of the data that we record is not necessarily immediately needed always and forever. We can do levels of interpretation. So if we drop down a slide, I think we get into a slightly different detector, but it's one that's closer to my heart. This is the so-called Cookiebox. I don't really want to explain where that name comes from. Let's just say it's historical with Jens Wiefhaus, who was one of the original progenitors of this thing. Essentially, it is an angular array of particle detectors. So I said I like to use lasers to blow things up. I blow things up in the middle of this device. And inside the middle of this device, all of the pieces come flying out. And from the pieces, I can reconstruct the chemical state of, say, the molecule that I'm interested in at the time that I was interested in, at the snapshot, the femtosecond within its reaction. And so that's what I want to use this device to measure. But this device produces almost an obscene. It's not quite as bad as those cameras that I showed you in the last slide, but in this slide, we're already today at the rate of about 10 gigabytes per second per channel. Now, this thing ultimately outfitted is going to be 20 channels. So we're talking 200 gigabytes per second. That's the raw data. That's raw digitized waveforms. That's not the information. The information actually looks much more like it would fit a language model style AI. And the input there would actually only be about 200 megabytes per second. Much more reasonable. And so our goal here with this particular detector is let's have a concrete example where we have a collaborating set of sensors. This collaborating set of sensors needs to pool its raw data so that it can extract this thing that is more on the scale of 200 megabytes per second, and then can actually produce inference output that tells the accelerator how to modify the photo injector, for instance. So it can send instructions 2 miles upstream to tell the laser up there that it needs to change its wavelength a bit or change the shape. Or it can move some of the motors that are inside of the magnetic. We use undulators to produce the X-rays, so it causes the relativistic electron beam to wiggle back and forth, gives off a big burst of X-rays. But we can move those magnets, and so we can change the shape of those X-rays that get emitted. And that's what we actively can control with the output of this device in real time. And so we need to aggregate all of this information from multiple sensors, also the sensors that are distributed up the accelerator, into a decision that is a control decision to enact at the millisecond data routing at the microsecond time scale. So we're pushing latency here. So if we drop down one more, I'll mention one of the collaborations that was recently funded, kind of using, just like Enterprise Neurosystem is, using this Cookiebox as a representative detector of where we have really high data rates today. We don't have to invent the camera. It already exists. And the models that we want to train to interpret those results are likely to be trained elsewhere, not necessarily at SLAC. And so we like this idea of having high-performance computing that might be at a remote DOE lab, for instance, at Argonne, at the Argonne Leadership Class facility, computing facility. And so they've got various resources there that we could use to do very rapid retraining. And we need the rapid retraining because, in fact, this is a real system. The time of day changes our accelerator. The floor of the whole thing buckles very little, but it does buckle over the course of a day. And our magnet temperatures change. There's a lot of things that in the hutch, essentially just from hour to hour, is constantly moving. And so you want to have the ability to update the models that are your twin of this system to on the scale of minutes at least. And that's where we really need very high speed training. So we plan that we have a good network connection to not only Argonne, but also over at Berkeley at NERSC. There's this thing called ESNet, Energy Sciences Network. We can use a pretty fat pipe. We can leak full fidelity data at a good rate, not at the millions per second, but we can do it at least at the hundreds or thousands per second. We can leak data for training. We can do fast retraining, which is this part of what was motivating this paper with the Argonne side led this bridge data center AI system with Zhang Chun. That paper really said that this is really a viable way to go. Instead of putting your training local to your sensor, leverage the HPC that lives in these high performance computing centers. And then all you really need is just your ability to apply the inference side at your edge. Now, I believe that maybe we could get a little smarter on our edge as well and not do only inferencing on the edge. And so we've been exploring some new hardware to enable that. But for most purposes, the heavy compute happens at the mothership. The tentacle spreads across the country. You have multiple experiments running at different labs that are potentially even related. Possibly they're not time synchronized, so you have to worry about that as well. And likely they spread across agencies even. Maybe they're not all DOE. Maybe some of them are different agencies in the federal government. And so this notion of security comes up because now we're spanning different sites. We're interfacing different organizations, different administrative units, and we have to handle this authentication and we have to handle access. And some things will be truly open, like the science that we tend to do at SLAC, versus other labs that maybe are not so open. And so that's where I think having some of these ideas that are more familiar in the private sector leak into the academic sector as well is quite important. And in fact, I think that's kind of the role of DOE. We're sort of this go-between between this more pure academia of university and the non-academic private sector. We're sort of in between. And I see it as kind of our responsibility to give these inspirational use cases that sort of show the country, here's how academia feeds directly to technological advancement, and it becomes something that is commercially viable that then can survive on its own. That's when our ideas really get born into the world and get to mature and survive on their own. And so that's where I really am excited about having DOE be this sort of example of here's how we build an inspiration case for this federated network of AI that crosses facilities. So let's drop down one more. I have a brief aside that is related to fusion energy. I only want to briefly mention this because this is really a key point to why I believe crossing domains is so important. It turns out that the model that we use, this transformer model that we have in mind for that Cookiebox interpretation, probably also works for a tokamak fusion reactor. And so if you look at what the sensors look like during a shot of the plasma and this is tokamak magnetic confined fusion reactor. So you have a plasma going around this torus, and you've got a bunch of sensors watching this thing, and you're trying to watch this plasma to see if these little crosses in the upper right that look like they intersect the walls, the bright things, the feathers that are going off, those are dangerous. Those send energy into the wall, and those destroy your machine. Not good if you're trying to make energy sustainable with a fusion reactor. So you want to suppress that. And it turns out that if I look at the raw data coming from those sensors and I apply essentially a Fourier mapping of it, the data actually looks very similar to what we're doing in the Cookiebox as well. And so in fact, the model's architectures look quite the same. The featureization stage is different, but the core models look kind of the same. And so we can apply some of our intellect together. And the other crazy thing is if you actually look at what these look like in frequency, it looks like music. The plasma sort of sings. And so that led to a whole completely unrelated collaboration with audio processing that Bill actually inspired by introducing me to someone who was in vinyl restoration. And so, I think this idea that you have cross-fertilization across really disparate domains is where creativity can come in. And, if you're stuck in your silo, it's really hard to see your way around an obstacle. You need the ideas to hop over the walls of that silo. And that's where I love this fusion example as a good case where X-ray science meets fusion science, and they can share a common architecture. Okay, so if we jump down one more, back to the main idea. So one of the things I'm also really excited about working, and why I love working also partnership in a co-design way with industry, is that there's a lot of novel architectures that are being created right now for AI specific ASICs. And the reason that looks so exciting to me, instead of just solving the problem better and faster, it comes to this idea of real co-design, where each algorithm is most likely going to have a more optimal hardware implementation for that algorithm. Whether you do in a CNN, which, obviously GPUs have dominated the market here, but, there are other architectures out there that in fact, might implement language models differently, or graph networks differently, or reservoir compute is another interesting route to go. So there are a lot of algorithms out there that could be better serviced by different hardware. And I think of each vendor really as filling a different niche, and that this really is an ecosystem of hardware. And if I have an ecosystem and I'm looking for a valid result, any one of them I don't think is actually going to give me the final solution. I really want to aggregate over all of them and take sort of a community consensus. And that community consensus should be over algorithms that are significantly different with each other. And that way I get maximum heterogeneity on solutions. And where they all agree, I know that that is likely the right choice forward, right path forward. And so it sort of maps nature a little bit better, that the way life survives is by having a very diverse set of solutions to the problem of survival. And that way you can evolve into a more successful solution. And I think our algorithms are the same, and they're mapped with the hardware as well. So the hardware is the same. We want a diversity of hardware that is available. And as soon as you make that statement, I want a diversity of hardware available for my problem, now you have this federated hardware issue as well. And so it leads to a lot of interesting complexity that not only from the machine learning research perspective, saying that I want the maximum diversity of different models to solve same and different problems, but also they will map to new and emerging hardware as we invent new ways to do compute. And these things need to come together, which means that the infrastructure and the science are actually woven together in this co-design concept. And that's what I like so much about this Enterprise Neurosystem, is it's not just an infrastructure organization. It's not just a research organization. You're really marrying the two together. And that's the way that it will really produce a result that is not only scientifically valid, because you'll suppress bias by having a diverse set of solutions, but also it's more in line with how nature evolves and how nature survives. And so that's what I'm so excited about. And so if we drop one more, I think I summarize. Oh, this is getting back to the what does the edge look like to me? This is actually just kind of a plug for what we've done at SLAC for the edge. Our notion is that we have hardware. The hardware that is certainly not exhaustive. We have GPUs, FPGAs that we are exploring actually inside the host nodes of our edge node. But we also have this coprocessor, the GraphCore Pod 16, is something that we're exploring as a way to implement graph neural networks, CNNs, and also these more language style models. So we're looking at both of those. I like the idea of having something at the edge that can train. It's not necessarily a requirement. We've gone quite a long ways with the FPGA alone. But when you start realizing that there's a lot of hardware emerging now that can do both inference and training in reasonable form factors that can fit at the edge near your sensor, or ideally, my real dream, take one of these chips and plug it directly into the sensor and do your inference actually on board. Eventually we'll get there. Probably not that far off either. So the edge is actually getting pretty interesting, and it's heterogeneous. And it's already heterogeneous, as in this picture. In our own lab, we have FPGAs, GPUs, and IPUs already sitting there at the sensor. So if we drop one more, we'll say what the core looks like to me. And this is on the high-performance computing and the cloud provider side. This is what gets very interesting. You no longer are using necessarily, you of course can use clusters of GPUs to solve your ML problems, but you also have these big other machines like the Cerebrus wafer scale engine or the Samba Nova solution, right? You've got also GraphCore has their larger Pod 64s. There's an awful lot of now somewhat bespoke AI ASICs that are specifically tailored to training that can live in the HPC. This is also a heterogeneous hardware environment, right? And so you also need to federate this, even though it's within the mothership, even though we're going to be submitting our jobs. Actually, That in itself is a problem. How do you submit jobs for a running experiment? You can't submit to a batch queue that will give you a result a week from now if my experiment is happening right now. So in fact, Bill, I think your job is significantly harder than you thought it was, because you're also going to have to coordinate how you schedule things as the needs on the edge change versus the resources in the core change. And so I think, this idea, I did say this thing about, I can't tell the difference between the edge and the core here. Nature took millions of years to figure that one out. We've got like 3. So let's figure out how we do this. And that's where I like to say this: use tailored optimal scheduling and flow is fun to say, really hard to attack. But the thing that's really cool about the Enterprise Neurosystem, I think you've got the team. I think you've got, because it's not one company, it's not one academic lab, you're really drawing on the privacy sector, you're driving on the enterprise sector, you're driving on the cloud services sector, and the networking, and the 5G, and telecom. So everyone is coming to play at this game, and we all have to, because no one person is going to find the solution. We have to work together. And that's what I think is beautiful about this ecosystem. It is in line. It's the computing version of macroevolution in the world, roughly. And so that's what I'm excited about there. So if we drop down one more, I think I can just end probably with this. I just took those initial slides that were very enterprise neurosystem centric and mapped them to science. And I'll just remind people, scientific advancement happens via competitive collaboration. Yes, we're competitors, but boy, do we like to argue with each other. And so, the stakes are significantly lower than, say, in the financial sector. However, we still fight like it's the end of the world if we're wrong. And so that respecting that competition, I think, is why security and access needs to be fundamentally built in from the beginning. Like I said, sharing model architectures across domains is really key. That's where innovation actually happens. I'm 100% certain of it. And from a cultural perspective, I can't speak for the business world, but I know in the science world, if someone is really close to what you're doing, it's very hard to collaborate with them. It's much easier to collaborate with someone who's attacking a problem that you're not. And so it's easier to work together the more distant you are. I guess we're fermions. Anyhow, innovation happens across large distances and unconventional domains being coupled together. I think that is something that we want to look at. I'm sure there's a biological analogy in there somewhere, Bill, with symbiotic relationships are not with individuals that are competing for the same food source. I'm sure that's somehow there's a parallel there. Let's see. And then this edge and core merging. This is where I think federated scientific computing really, really would shine. At some point, I think it is there was this grid computing effort that was supported early on by DOE, and I think that's still maybe a bit of a dream that can help here, or at least should be coming to fruition, where you don't realize that you were leveraging these heavy resources. They're just automatically leveraging for you, right? Each individual organism in an ecosystem doesn't realize how the whole food chain is actually supporting its existence. It doesn't have to realize that. It just is. And that's kind of what we want for this federated network of compute across the world, actually. I think smaller, just DOE. I don't think global, but eventually global. Excuse me. I really like this idea of a primary intelligence. In a sense, if I pull back on my hippie college days, that's Gaia, isn't it? That's this intelligence that is, everything moves forward in the end. And we want something to ensure that we're moving forward in the end. And at least within DOE, that's its role. DOE's central role is to make sure that our sciences, at least our energy sciences, move forward. And we're going to build a network and a central intelligence and an interconnected web of tentacles that ensure that overall we move forward when it comes to energy in this country. And that's our federal responsibility with DOE. And then again, I already spoke, I think, about the teleco and scientific community having sort of this interconnection that we as scientists can't live without this infrastructure that needs to exist. And the global scale, I would say, to me, is more than just climate change. I think it's our response to climate change, not just to how to solve it, but how to live with it. And that involves agriculture. It involves our energy production and seeking novel energy sources and how we load balance when you have fluctuating sources. That's another global scale issue. Essentially weather prediction comes into that as well. So I think there's a lot of places where this overall AI infrastructure can help. And I think that we don't tackle any of these problems unless we have this ecosystem built. So with that, I think I'm ready to open up. 2 questions. Or Bill, if there's something that you just are dying to get out. Excuse me.
I just want to thank you for your time today. That was fantastic. And what drew you to joining the Enterprise Neurosystem? I'll just ask one question and then we'll open it up to all the other ones. But I think getting you involved was fantastic for us and really made us look at this kind of architecture in a very different way and also realize how energy sciences play such a huge role in solving potentially climate change and the kinds of pursuits you have. How would you describe your engagement and what have you enjoyed about it?
Well, I think, when I first got introduced to you and you explained what Enterprise Neurosystems was trying to tackle, I was getting, it was right at that time where I was seeing the power of federated machine learning. And I also have some collaborators that are for instance, at closed labs where they aren't allowed to share. And so this concept of how you build a network of different levels of privacy and security was something that I, haven't had to deal with and is interesting. And I can see that there are a lot of domains that would benefit from something like federated machine learning, but they're a little nervous to share. And so having the infrastructure and the network built such that we could share will allow me to pull these colleagues into my collaborations more directly. And then we can actually leverage each other's insights. Because again, they're not doing the same science domain as I am, something else. However, our models look quite similar and our use cases are almost complementary. And so if we could do federated ML, boy, it would really give mutual benefit to both of us. But that's currently not enabled. I don't know how to do that. And at least what you've proposed, I think, is to get at that solution. And I see in the question section, there's a question about diminishing returns for transfer learnings if it's across 2 disparate of domain. I can see that problem that if it's almost like that's a hyperparameter you want to tune. Because if I think about what I'm going to be encouraged to do with my own models, is I will probably imagine I'll have a suggestion engine pitching to me that, well, if you alter your architecture slightly, there's this other group who has data that you could actually leverage as complementary to your own, for instance. But if you don't, if you insist on using your own architecture that has no bearing on this other science as well, then you don't get to use their data. And there's got to be some sort of value to that like, if I'm firm that I know exactly how to architect my solution, then I don't need federated ML. But maybe I can put a metric on there that if your suggestion is really strong and there's a chance that you give me a really new insight, then I'm willing to listen to you. I think that's how you control this idea of how open or how exposed you are to these diminishing returns if you enforce full disparate cross domains. And really, I think the business of this mothership that Bill sometimes talks about, this central AI management, is maybe not so much to enforce that everybody play together, but instead identify players that have correlated or similar problems and that are likely to get along and are likely to play well together. And so maybe it's less so that we're forcing these central models to be applicable on all domains. What maybe this ecosystem is doing is saying these two domains have related and complementary problems. If they combine forces and train the central large model, like large transformer model, for instance, and then just tailor it to their specific, this now is a more valuable pre-trained model that actually could benefit this domain over here as well, or this domain that these two originals were not even aware of. And so that's what I like about this idea. It's not that we're forcing people to play in a giant sandbox. It's that it's a tailored sandbox, and we try to encourage things that are more generalizable. And so I think that's how I would answer that diminishing returns question personally. Equity. Oh.
You're reading the second question here?
I am.
From Lay.
Yeah. Whew.
It's a good question.
Hey, Bill, you want to take that one?
Can you read me the question? I'm looking at it right now.
Okay.
What mechanisms and methods are envisaged to address equity of access? Part of one. Second part of the question is, how can this avoid creating a cartel of knowledge and data access organizations based on their existing financial resources?
That's excellent questions. And I think one of the working groups that we have actually is a ethics and I guess you could say ethics within the application working group. And we're just getting that started now, but it's always been part of our guiding principles. We're taking a look at a variety of different ethical frameworks. And I think I'm addressing the first part of the question in its spirit, is to basically look at the kernel level of this intelligence and the operating principles that will be guiding it going forward. Because I don't want to get too esoteric, but I see how powerful it could become down the road. And that's always been something we've taken into consideration. We're going to take a look at a number of different philosophies and approaches that don't favor any one particular ethos or practice of any kind or any culture of any kind. We want to make it as ubiquitous as possible in that approach. But also, beyond that, the access is so critical. And one of the architectural parameters we've already started implementing or plan to implement is to take the models and move them to the data from data source to data source to data source. So the data remains resident. We all realize on this call how valuable that data has become and how problematic it can be as well in terms of access. Everybody gets to retain their own data. The models are shared. The models can be used by whoever the participants are within the paradigm. And access to that from an open source perspective, to me, is absolutely paramount. It has to be accessible to all. And from an open source perspective, the transparency of those models and their creation and the ethical guidelines that drive them, all of that, it's going to be very interesting as we go forward. There are going to be new architectures that are going to emerge that I think will help enable that. But the whole idea is to provide that universal access to all these models within the framework that we've created. And so it really is the upstream open source model, you could say, not AI model, but the business model or the creation model is probably a better term. And then from there, people can take it and do with it as they will. But that access would be, everybody who's a member, everybody who wants to be involved, and that membership is wide open. So I don't want to be too egalitarian, but that is the vision. That's how we
pretty egalitarian.
Yeah.
I have a feeling there are a few domains that might be a little nervous about that.
Oh yeah, I'm sure. But I think it's to degrees. I understand. Okay. Yeah, I understand.
One of the interesting things that has come up, I think, front and center is not just for data, but also for models, provenance. Data provenance is absolutely critical for the sciences, and we want to track that. And something that was also rather an interesting concept that came up, I think, fairly recently, Bill, in one of our talks, one of our discussions, was this idea of the intention of the data producer. And somehow respecting the intention of the data producer was quite interesting to me. And so this, I think, maybe gets a little bit about The provenance allows you at least to track whether a cartel is emerging, for instance, on both the data and the model, right?
Correct,
Because the
yeah.
models will have unique identifiers as well as the data will have unique identifiers. So you could at least, I don't know that we have the solution. Bill, that's what the ethics committee is about, is to how to develop a solution. But at least the IDs are there. At least the provenance record and the tracking is recorded. So you've at least got a metric that you can watch to see if this is something that is emerging, and if it is, you can address it. And so that's something that I think at least the hooks are there to address that question. Yeah, and that's my hope.
Correct. And I also think there are going to be degrees of access that will be enabled by security requirements, I think. We're definitely going to be looking at that as well. But in terms of the sharing of models and in terms of the data that has to be both protected but also utilized to train the models, we're looking at the different kinds of architectures that can be used to basically enable that. And that's really part of the solution. So, yeah.
And that's, I think scientists have that same concern when we produce data. I mean, we pour, I think one experiment is 1 week on our X-ray laser, and it's of scale $1 million. So it's like a 3-year grant from DOE just to get a single experiment, right? And so when you're investing that much, the data that you produce in that experiment, you hold dear, and you want to get that publication. And so your data access, you want embargo on that data. And so you want to embargo it to your core collaboration first, and then you'll open it up. But DOE's perspective, much more to Lee's point, is the data that the taxpayers paid for. That belongs to the taxpayers. And so the whole nation should benefit from this. But they also realize that if they make it completely open immediately, then the academic folks who are trying to get tenure don't have an incentive to actually do the experiments, because they'll just get scooped by people who already have tenure. And so there's a tension there. And that's something that I think these facilities, and why it's interesting to have a DOE example be a part of this neurosystem use case, because it is at this tension of you really want to and must be open ultimately, but you also still want to incentivize the actual data producers. How do you navigate that? And so I think that also gets to this as well. It's an interesting problem.
It is, definitely.
I don't have the solution. Tenure for everyone.
Across the board.
Across the board, tenure for everybody.
There you go.
Everyone's tenured.
Right.
I'm not seeing any additional questions here in our queue from the audience. We'll get in another moment. But my goodness, quite a tremendous presentation, gentlemen. Just a lot to unpack there. Amazing.
Very fun.
My BFA in theater is shortcoming in a lot of this data. So,
hey, software is art, right? So
right.
None of us get any of this done. And this is one of the secrets that drives, I think, a lot of young physicists nuts, is that if you have experience in the theater, you're going to be more successful. In the end, you got to get funded. And so there's a lot of people skills that just don't get taught in physics grad school, but really serve you well.
The unconventional alliances, right?
Mm-hmm. Yeah, exactly. Cross-domain alliance.
Cross-domain.
Isn't that what we need?
We need cross-pollination to make the world go round.
That's right.
Terrific. Bill, Ryan, incredibly helpful and insightful presentation. And thank you both for your time.
Absolutely.
Thank you so much.
My pleasure. Thank you for having us.
Hope we see you in the future.
Absolutely.
We're going to take a short break. I am going to prepare to bring Ana Maria Estrate, our research scientist from the Chan Zuckerberg Initiative, to the stage. But I thank you both for your tremendous input and look forward to seeing you again.
Great.
Thanks so much.
Thanks.